Okay, hi Year 12. So here's a quick video on looking at 5i, integration of the reciprocal function. So what we're looking at here is we're not actually looking at integrating a log. We're looking at integrating something that looks like a log, that's been differentiated, and we want to make sure we're getting it into a particular kind of form. So I'll read through here. It says reversing the standard forms for differentiating the log function gives the standard form for integrating them. So remember, when we go one direction, we're differentiating, and we go backwards, for that same thing, we're integrating. So the same kind of idea that we're going to use for this is what we used for the reverse chain rule. Interestingly, this now allows us to handle integrating x to the minus 1, which I'll show you in a minute what I mean by that. And we're going to note that there's an absolute value around the integrated form, and I'm going to explain why we've got that in a second. So before I read through any more of that, let's just make it in a little bit more detail and have a look what I mean. Okay, so let's get that colour pen there. Okay, let's have a look at the parts you've got in the boxes here. And we've got the standard forms for integration. So let's have a look across the top here. We learned a couple of lessons ago that when we differentiate something that looks like log of x, so log to the base c of x, we end up with something that is of the form the derivative on the function. The derivative at the top and the function at the bottom. So remembering, here's our function x. If I differentiate x, I end up with 1, and that function x goes back on the bottom. And we wrote it also in the form under here. So if I differentiated log of f of x, I'd get my derivative of that f of x on the top and the function on the bottom. So that's what we've looked at previously. Today, what we want to have a look at is integrating something that looks like 1 over x, and we're going to end up with log of x as our solution. Now, I'm just going to move over to the side over here because I want to show you something. So if I integrate 1 over x dx, what that actually is x to the minus 1 dx. Okay, we know that. We're quite good at that now. Now, using our rules for integration, what I normally would do would be add 1 to the index, divide by that new index. So if I do that, I would end up with x to the, what do I get when I add 1 to minus 1? I get 0. And then I divide by 0, which is not possible. So when I get something, when I try to integrate it that looks like I'm going to end up with a 0 and a 0, I actually am looking at a log. So log to the base c or L of n. So let's scroll back over here. So when I have something like, I'll just scroll down a little bit there. Okay, something that I want to integrate that looks like a derivative on a function, what I'm going to end up with is log of that function plus c. For example, if I'm going to integrate 1 over x with respect to x, I know I have my function. If I differentiate this x, I end up with 1. So I've got something that looks like the form derivative on the function. So I can say that my solution is log of that function plus c. Now what you will notice is there is an absolute value in here. Okay. Now we need to have a look at why that absolute value is happening, because the funny thing is, and I'll draw a graph over here, what we're doing is we're talking about two different things with two different domains. We're talking about this 1 over x thing here, which is a hyperbola, and that can happen for all values of x except for x is equal to 0, because we can't divide by 0, and we know we've got our asymptotes here, which are our x and y axes. But then we're looking at, when we integrate that, we end up with a log of x. When I change my colour, my log of x is going to look like this, which is only valid for positive values of x, because again, it's not going to cut the x value. We can't, the y axis, because x can't equal 0. So we've kind of got this strange thing happening here. And what a lot of people say is, well, why do we, when we integrate 1 over x, so this part here, do I have to pop in an absolute value? And a lot of people say, well, that's because we can only have positive values of x, so that disappears. Or the negative values, so we only want the positive values. Yeah, that's true, but it's also not why we do it. So we need to understand it a little bit differently and have a look at what happens when x is positive and when x is negative. So I'm going to explain that to you now, just down here. Okay, so when we differentiate log of x, we end up with the derivative on the function, which is 1 over x, and that is valid in the domain of all x greater than 0, all positive values of x. Because we're looking at log of x here, we're going to end up with 1 over x, and we're only looking at positive values. So if I reverse that, so from a differentiation this way, integration the other way, if I now integrate my 1 over x with respect to x, I know that I'm going to end up with log of x plus c. Okay, so here, just recapping that, log x is defined for values greater than x. But we also have a possibility where log of x is defined for minus values of x. I'm just going to change my colours again. And that would be, where we'll be looking at differentiating log of minus x. So if you're unsure what log of negative x is going to look like, that's going to look like, I might draw that in another colour up here, green. It's going to look like this. And so this log of negative x is defined for negative values of x. So what is the derivative of log of negative x? Same way as we did up above, it's the derivative, which is minus 1, on our function, which is 1 over x. And that occurs for x less than 0. So we've got this funny thing that's happening, is that we've got that the derivative of log of x is 1 over x, and we've got that the derivative of minus x is 1 over x. So I can make an integral from that as well. So going backwards, therefore the integral of 1 over x is equal to log of minus x plus c. So when I'm integrating 1 over x, I've got two different versions here. It's equal to log of x plus c for x greater than 0, but it's also equal to log of minus x plus c for x less than 0. So I have this funny thing happening, and this is where our absolute value comes in handy. So how I'm going to write that is that the integral of 1 over x with respect to x is equal to, it's equal to log of x plus c when x is greater than 0, and it's equal to log of minus x plus c when x is less than 0. And it's a piecewise function really then, isn't it? And this way that I've just written it, this piecewise way, is really how we're defining the absolute value function. So if I join those two together, I'm basically getting log of the absolute value of x plus c. And that's why we do it. So I want you to think about that, and I'm going to go back and rework these questions with you, and we're going to pop the absolute value in them this time. So let's do that now. Okay, so let's just have a look at this first one here. We want to evaluate the following expressions. Now I'm integrating 5 over x with respect to x between e to the power of 2 and e. Now, what we're going to think of when we're doing these questions is I have an x on the bottom line. If that was written up the top as a minus 1, I add 1 to the index, oh, I get 0. It doesn't work. So these are our logs, okay? We have what our solution is. We have 5 times the size of what we would originally want it to be. So we basically have, I'm going to write it out like this, put my 5 out the front, e to the 2 on e, 1 over x dx. I've now written this in the form of the derivative on the function. So the derivative of x is 1, my function is x. I pop the 5 out the front, so I've got 5 lots of my derivative on the function form. So what I can do is say, well, I know that when I integrate 1 over x, and it's in the form derivative on the function, if you have a look back at your rule up here, I'm going to end up with log of f of x. So I'm going to have 5 lots of log of the absolute value of x between e to the 2 and e. Now, because in this case the x values that I'm going to pop in there, the e squared and the e, are positive, it doesn't really matter that I have whether I have that absolute value in there or not. Because if you think about what we just talked about with that piecewise function, when x is greater than 0, it's going to work out as just log of x anyway. But I'll pop it in, leave it in there. So it's going to be 5 lots of log of e to the power of 2 minus log of e. Now we need to neaten that up. A couple of ways to do it. Let's just use log laws and go log of e to the 2 over e, which is 5 log of, we've got e2 over e, which would just be e. And remember this is base e, that's saying that this log, we've got base e to the something gives me e, it's 1, so it's 5 times 1, which is 5, and that's my first answer. Let's have a look at the second one. Okay, here we are integrating between 4 and 1, 1 over 1 minus 2x dx. Okay, so we've got something that's going to end up being a log, because if I had this up the top to a power of minus 1 and added 1 to the index, I'm going to get a log. So let's make it look like the derivative on the function to start with. So, oops, I'm not going to put that one there, sorry. I'm going to write this in the form the derivative on the function. So here is my function on the bottom. What's my derivative of that function? It's minus 2. That's what it would look like if it was derivative on the function. We have a 1 at the top. I'm minus 2 times as large, so I need to pop a minus a half down there. And in essence, this minus a half and this 2 would be cancelling each other out to get us a 1. But we need to keep it in this format because I can integrate something that's of the form the derivative on the function. So I'm going to have minus a half, and having a look back at your rule, log of my function, which is log of 1 minus 2x between 4 and 1. Now I'm going to change those little lines there to an absolute value, because in this case, when I pop my values in, I'm going to get a negative in there, and so my absolute value is going to be necessary. So minus a half, I'm going to have log of, in the first case we're going to have the absolute value of 1 minus 8 minus log of the absolute value, popping 1 in, 1 minus 2, which is minus 1. Okay, let's just neaten that up a little bit. I'm going to have minus a half there, log of, sorry, that should have been log of, we had 1 minus 8, which is minus 7. I apologise there, sorry guys, it's late at night at the moment. So 1 minus 8, which is minus 7. Log of minus 7 is just going to be log of 7. I'm going to take away log of minus 1. That was right. Let's double check that. 1 minus 2, which is minus 1. Yep, which is log of 1. And I don't need the absolute value, sorry, because I've actually already used the absolute value, haven't I? I've gotten rid of the minus 1 and written a 1 in there. So that's going to be equal to minus a half. Log of 7 is log of 7. Oops. And log of 1, well, that's saying that's e to the what gives me 1. It's going to be 0. So that's minus 0. So the answer is going to be minus a half log of 7. Okay, the next one I've already worked out. It's fairly simple. I'm going to evaluate the expression between 1 and 0 of 2x over x squared plus 2 dx. Now, we need to just practice by having a look at our functions that are under the integral sign. And if you have a look at this, you can easily see that we've got a function on the bottom, and if I differentiate that function on the bottom, I straight up end up with the derivative on the top. So it's a nice easy one. So when I integrate this, I'm going to straight up end up with the log of x squared plus 2 between 1 and 0. Now, I should have an absolute value sign here and here. I haven't popped that in there because I can straight off see that when I pop my 1 in and my 0 in, I'm not going to end up with a negative in there anyway. So I haven't put it in there, but it probably should be in there. I'm popping our 1 and our 0 in. We're going to end up with 1 squared plus 2, which is 3. So log of 3 minus log of 2. I'm using my log laws. Pop that in there. Knowing that when I minus my logs, I can divide the functions that are in the brackets, and that's my answer there. So that one's fairly straightforward. This one is not that difficult either. So we've got an integral between 5 and 4 of x over 9 minus x squared dx. Now let's start by, we know it's a log, okay, because obviously we're in a log topic, but I can see that if I differentiate my bottom line, I end up with minus 2x. My top is very similar to that. So what I'm going to do is write it in the format of my derivative on my function. Okay, the derivative 9 minus 2x is minus 2x. My function is 9 minus x squared. And I can see I've got minus 2 times the size of what I had up here, so I need a minus a half out the front. What I need to now do is pop it in log form, and what I'm going to do is I'm definitely going to make sure that I pop my absolute values in this case, because I am going to end up with, and I guess let's just make a blanket rule that we put our absolute values in anyway so that we don't have to think about it. But I'm going to end up with log of the absolute value of 9 minus x squared. Popping that in, my value's in. Let's do that. Minus a half, and we're going to have log of 9 minus 25 minus log of 9 minus 16, which is a minus a half of log of 9 minus 25 is minus 16, so that gives us 16 because it's the absolute value, minus, oops, I'll fix that up there, minus log of 9 minus 16, which is minus 7, but I'm taking the absolute value of that, so that is going to become 7. So my solution is going to end up as minus a half log of, I'm going to use my log laws, 16 over 7.